Today I'm going to show you how you can take a mathematical situation and translate it into a couple of different common formats. The three formats we're going to deal with today are graphs, equations, and tables of values. Please excuse the handwriting. So graphs, equations, and tables. Let's take a look at our first situation. So it says Bella planted a rose bush that was 20 centimeters high. She watered it daily and measured its growth each evening. She found that the rose bush grew about a half a centimeter every day as long as it was watered. So what we're going to do first is we are going to take this situation and we're going to turn it into a table of values. And when you have a table of values, you're going to have your two variables going on here. Our two variables that we have going on here is that she's measuring, first of all, we've got height, obviously, because she measures the height every day. And the other variable that we have going on is the amount of time that passes. So the amount of days that go by, because she measures it every day. Now, you might wonder why I'm putting time here on the left and height on the right. Well, because it's kind of a mathematical convention that we normally put the independent variable on the left and the dependent variable on the right. If this does not sound familiar to you, please go back and look at some of our previous videos about why the independent is X and why the dependent is Y. There's some good stuff on in our scatter plot discussion that's shown previously on this website. So, in our time. So, when Bella very first plants the bush, okay, that means that no days have gone by yet, and it's 20 centimeters high. I'm going to label it here so we know we're talking about centimeters. So day 0, no time has passed yet. When she first plants the rose bush, it's 20 centimeters high. Okay, after she waters it at the end of one day, okay, because she found that the rose bush grew about a half a centimeter every day. So that means that at the end of day 1, it's now 20.5 centimeters. So if it grows a half a centimeter every day, that means at the end of day 2, it's now 21. At the end of day 3, it's now 21.5. We could go on and do this all day long. I'm going to stop here because technically I could keep going for a long time. So my independent variable is my X variable, goes on the left. My dependent variable, so my independent variable is the number of days that it's watered. My dependent variable is the height. That means how many centimeters tall the plant is. So we've just taken this information and we've turned it into a table of values, which sometimes you will do. It's important to note that, you know, technically there are other values here in between. For example, some people might argue, well, if it grows half of a centimeter in one whole day, well, then in half a day it grows a fourth of a centimeter. So that's true. There are a lot of other possible values that are in here that we have not accounted for in our table of values. And a lot of the time it would be pretty much impossible to write them all. Frequently when you're asked to make a table of values, they'll just ask you for, you know, 3, 4, 5 possibilities, and it's frequently impossible to write all of them. Okay, so our next step is that we're going to take this information and we're going to turn it into a graph. And so I'm making myself an axis here. Now on a coordinate grid, when you graph points, technically you could account for negative and positive or negative amounts also, but I'm just going to use the first quadrant here because we're talking about height and we're talking about time, and we don't have negative height or negative time. Okay, so even though the regular coordinate plane looks like this and there would be 4 sections that we'd be graphing in, we're just going to use the first quadrant right here where all the values are positive, just like we would with a scatter plot or a line graph. Okay, I got to decide what my appropriate scale would be. So as time goes by, remember our independent variable is days. I'm going to put it here along the x-axis. I'm just going to do 1, 2, 3, 4, 5, 6. I'll do 8. Okay, and so now I got to decide an appropriate scale for my height. And which is my Y values. Since it's going up by a half a centimeter each time, I think it would be appropriate to go ahead and have my scale increasing by a half of a centimeter each time. So I'm going to make a little break right here on my graph to indicate, yes, I know I'm not starting at 0, because that would be a whole lot of space that's taken up unnecessarily, because the very first height that I have is 20 centimeters. So I'm just putting a little break right here on my graph, and I'm starting at 20 centimeters, then 20.5, 21, 21.5, 22, 22.5, 23, 23.5, this will be enough, 24. So I'm going to start graphing my data. So day 0, absolutely no time has passed. It has just now been planted. So 0 over here on my x-axis for my number of days. I'm going to go up to 20 centimeters because on day 0, hasn't had a chance to grow yet. It starts out as 20 centimeters high. After day 1, it's now going to be 20.5 if it grows by a half of a centimeter each day. Day 2, it's going to be 21. By day 3, it's going to be 21.5. By day 4, 22, etc., etc. I could keep doing this all day. You'll notice I've got a nice little plot right here. Now, some people get confused as to whether or not they should actually connect the dots. Now, very mathy term here. I'm using the word dots. Okay, whether or not they should actually connect the dots when they are graphing information to make it a line graph or to make it a scatter plot. Now, when you are connecting your data points with a line, so like this, you're basically saying it's possible for there to be all the values that fall in between of these data points. So what I mean by that, for example, is if I could add another little data point right here. So that means after half of a day goes by, this is about 20 1/4. Okay, because it hasn't gotten a chance to go the whole half of a centimeter tall yet. Or after 1.5 days, this is about 20.75, because if you go directly over from here to here, it means that that's a possibility. Okay, well, that's entirely possible. We can have half of a day. Okay, we've talked about, that you can have 12 hours, which is half of a day. And you can also have 20.25 or 20.25 centimeters as well. So actually, because all these little data points in between are a possibility, okay, if I put my little data point right here, it's where it matches up with the days, it is possible to have half of a day. And where it would match across right here, well, it is possible to have in between 20 and 20.5 centimeters. We do fractions and decimals of measurements all the time. So this is a case for this graph where I would actually connect my dots because the values in between them are all possibilities. You can have a fraction of a day. You can have a fraction of a centimeter. So I'm going to connect the dots. Let me show you an example of where you couldn't do that really quickly. Let's say, because that might help make this a little bit more sense. Let's say I was keeping track of the, where did I put it? There we go. I'm keeping track of the points that are being scored at a basketball game. And as time goes by, okay, so here's my number of minutes I'm watching the game. These are the number of points that are scored. So after 1 minute, for example, 2 points have been scored. After 2 minutes, 4 points have been scored. 3 minutes, 6, etc. If I were to connect the dots here, I would be saying that all of these values in between are possibilities. Now, if I were to go straight down, it's possible to have 1.5 minutes, okay, which is what would be here. However, the data value directly across from it falls right in between this 2 and 3 at 2.5. Okay, I don't know about you, but I've never been to a basketball game where you can score 2.5 points, which is if this data point were allowed to exist right here in between. Okay, that's not possible. So that means if I were graphing the number of points that were scored during this game, I would have to leave the data points just unconnected. Okay, so I had it 1 minute, I scored 2, at 2 there were 4, etc. Because by connecting these dots, that means that any of the values in between the dots are possible. And if I go straight down here, yeah, I can have fractions of minutes, but I can't have, for example, if a data point were allowed to exist, whoops, right here in between the 4 and the 5. That would be saying you could have 4.5 points in a basketball game, which we all know that you can't. So there are some cases where you can graph the data where you got to just leave it as a scatter plot and you can't connect the dots in between. Now, the example that we're dealing with right now does not happen to be one of those examples. Let me go back to that. So we've connected the dots. So now, and I'm going to add a little arrow to the end of this line just to let us know that for really, I could sit here and keep adding values all day long if I wanted to. I could keep going, keep going, keep going, keep going. But so this little arrow right here is here to demonstrate the fact that technically this line extends, because I could sit here and keep graphing points all day. After 8 days, she's at 24. After 9 days, 24.5. Excuse me. I could keep doing this all day long. And so this little arrow is just to let me know that technically this graph extends. Notice there's not an arrow going in this direction, because if I started going in this direction, past the 0 to the left, that means I'd be going into negative minutes, okay, and or negative days, sorry. We all know there's no such thing as negative days. So now I'm going to point out some important terms for you that you really need to make sure you know as we're transferring this stuff among graphs and tables. First of all, let's look right here on the graph. And there's a special word for this 20 that we started out with, and it is called our initial amount. When you hear the word initial, like it was initially, oh, I meant to highlight it instead I scratched it out. When you hear, well, I was initially living in Hopkinsville, Kentucky, but now I live in Louisville, Kentucky. Okay, it's initial. That's like where you start out. So initial amount is what we start with right here. Okay, she planted a rose bush that was 20 centimeters high. That means from the get-go, it's just started. So the height to begin with is 20. There's also a more mathy term for this initial amount. It's what we call a Y-intercept. And the reason we call it a Y-intercept is because this is the spot where the data hits the y-axis. Let me show you another example really quickly. Okay, let's say that my class, oh my gosh, you all are the best kids ever. So I've decided that I'm going to start paying you for your good behavior. Boy, if only, right? So the second you walk in the door, I immediately hand every kid $5. Then, for every minute that you're good, I pay you an additional $1 a minute. Okay, so if I were going to make a graph of that, okay, let's say 0 minutes have passed by, okay, you guys automatically have made $5 because the second you walk in the door, okay, no time has passed whatsoever yet. I've automatically given you $5. So $5 is the initial amount in our little classroom management experiment. Okay, that's the initial amount. That is what you get the second you walk through the door. Okay, that $5 is also called our Y-intercept because it's actually where we hit the y-axis. So $5 is our initial amount, but the more mathy term for it is Y-intercept. Okay, so let's go back to where we just were. All right, so our initial amount, our Y-intercept here is 20. Okay, then we also, another important term that has been mentioned in a previous video, but it's definitely important enough to mention again, is what we call our rate of change. Hopefully you're all sitting at home thinking, oh yeah, that's also called the slope of our graph. Okay, rate of change or slope is the math term for our rate of change. And what we do is we examine the difference between two data points on our graph, and we figure out how they changed horizontally versus how they change vertically. So it's just like when we did transformations previously. Okay, if I were going to hop from this point right here up to this point right here, whoop, I hopped over 1 to the right because I hopped from 0 to 1. So 1 to the right, which we know from our transformations unit that a hop to the right is positive. Then whoop, I hopped up 1. Now be careful because my scale, I didn't hop up 1 unit. Okay? I actually hopped up 1/2 because my scale over here is going up by 1/2 every time, 20 to 20.5, 21 to 21.5, etc. So I actually hopped over to the right 1, and then I hopped up 1/2. So to get from this point to this point, I hopped over to the right 1 and up 5. Okay, our rate of change, or our slope, if this doesn't sound familiar, please, please, please go back and look at review materials, is determined by rise over run. It's our shortcut way of remembering it. Okay, that means what our vertical change is over our horizontal change. So in this case, it went up by 0.5, and it went over by 1. Because it was to the right, that's a positive 1. Because it went up, that's a positive 0.5. So that means our rate of change, or our slope, is a 0.5 over 1. Remember, if what I just said about slope doesn't make sense, please, please, please go back and look at some previous videos. Okay, but rise over run means our vertical change over our horizontal change. So now I'm going to go back. How in the world does all this help me to turn something into an equation? Well, you're getting ready to find out. So I'm going to ignore the graph for just a second. I'm just going to look at the situation, and I'm going to turn it into an equation now. So she planted a rose bush that was 20 centimeters high. She watered it daily and measured its growth each evening. She found the rose bush grew 1/2 centimeter each day as long as it was watered. So I want to find an equation to represent this situation. So it started out as 20 centimeters high, plus it grows 1/2 centimeter, or 0.5 centimeter, every day that it's watered. So if I multiply 0.5 times the number of days that it's watered, add it to our initial height, what we started at 20, that's going to tell us how high it is, right? The final height is determined by what it started out with originally, 20 centimeters right there, plus we're going to add 1/2 centimeter times the number of days that we are watering this rose bush. So, for example, if we let it grow for 2 days, I would multiply 1/2 times 2, which means it grew 1 centimeter. 20 plus 1 would be 21. That means the new height would be 21. Okay, so this looks right for sure. Okay, whatever our height is, it's equal to the original amount plus 1/2 of the centimeter, which is what it grows every day, times the number of days that it's allowed to grow. We've written plenty of equations in class before. But now I need to make it a little bit more mathy because this height and day stuff isn't going to work. Okay, height we refer to as our dependent variable. That's why it was on our y-axis. And our number of days is our independent variable. That's why it's on the x-axis. So instead of height, I'm going to write in my equation y, because height is our y variable. So whatever our height is, y, is equal to 20 plus 0.5. You can probably see where this is going. Number of days is our x variable that's on our x-axis. So I'm going to change this to 20 plus 0.5x. So my height, which is the same thing as my y value, is going to be equal to our original amount plus the amount that it grows each day, or the amount that it changes each day, times the number of days, which is x. So I'm going to take this equation that we just wrote, and I'm going to move it over here to the equation for a second. because I've noticed something kind of interesting. I'm going to write our equation right up here that we just found. Okay, so our height, or y, is equal to 20, our original amount, plus 0.5 times our x value. Anybody see where this 20 and this 0.5 is anywhere in our graph? Well, that's interesting. 20 in our equation is the same thing as our initial amount, which is our y-intercept, and this 0.5 is the same thing as rise over run, because 0.5 over 1 really simplifies to a 0.5. That's very interesting. So you can and this actually works for every single equation. This equation right here has a very special format. It's called slope-intercept format of an equation. Okay, and we actually normally see it written like this. I'm going to get rid of my labels here for a second. Normally we see it with the slope written first, and then the y-intercept written after. Why is it called slope-intercept form of an equation? Well, look, it's got the slope, or the rate of change, and the y-intercept, or the initial amount, all right here in the same equation, slope-intercept form. Let's look at another example just to make sure that that really happens for all of them, because that's pretty kooky. Okay, but you can actually write an equation based on the situation and that it actually matches up with the graph. So notice the equation, our original amount plus 0.5 times the number of days. This 20 matches our initial amount on our graph, or our y-intercept. That 1/2 matches our slope. Let's see if that happens for every situation. So let's see if that works for every single situation that we could have. All right, sorry, I was just on the wrong one. So let's see if this works for every single graph we could possibly encounter. So it says a pot of water at a temperature of 25 degrees is placed on a hot burner. The temperature of the water increases at a rate of 15 degrees per minute. So let's write this just as an equation first. So a pot of water is at a temperature of 25 degrees before it's placed on the hot burner. So that means it's going to start out at 25. Then the temperature of the water increases at a rate of 15 degrees per minute. So that means that we're going to add to the temperature 15 degrees every minute that it is on the burner. So our initial amount is 25 degrees. That's what it starts out at according to our situation. Plus, it's going to increase by 15 degrees times the number of minutes. So, for example, if we leave it on there for 3 minutes, well, 15 times 3 is 45. So that means, that's how we would figure out what the new temperature is. So the temperature is determined by taking 25 and adding it to 15 times the number of minutes that you leave it on the burner. Let's make this a little bit more mathy, because right now the equation we've written isn't very mathematical. Okay, so we've got two variables going on here. We've got temperature, we've got number of minutes. For reasons you can review on our website, the temperature is going to be our dependent variable, which means it's going to be the y variable. The number of minutes is the independent variable, which means it's going to be the x variable. So that means that our new equation is going to be 25 plus 15 times x. We multiply 15 times our number of minutes, add it to 25, that will give us y, that is whatever our new temperature is. Now, I should mention that even though you're going to see us pretty much using x and y all the time, and your textbook is going to do the same, that's only because mathematicians have just kind of agreed that the x-axis and the y-axis have certain meanings. Like x is your independent, y is your dependent. Really, in the grand scheme of things, does it matter that you're using y for temperature and x for minutes? Not really. It just makes it a little bit easier to interpret what you're talking about. Okay, so now I'm going to graph our data that we have here. So the pot of water was placed on the burner at 25 degrees. So right here, time. Okay, so no time has passed yet, and our temperature is 25 degrees. Okay, it increases at a rate of 15 degrees per minute. So that means that after 1 minute has increased, we're going to add 25, which means now it should be at 40 degrees. After 2 minutes have passed, that means it's going to be another 15 degrees hotter, which means it should be at 55. After 3 minutes, it should be at 70. So I really could keep adding these all day long. Now, do I connect and make this a line graph, or do I leave it as a scatter plot? Well, remember, if I connect, that means that all the values in between each data point are possible. Well, can you have half of a minute? Sure, you can have half a minute. We do it all the time. We don't do things in full minutes a lot of the time. So, yes, you definitely could have a half of a minute. If we look at our data point below right here, half a minute. Could you have between 20 and 30 minutes? Well, sure you could. Or, I'm sorry, between 20 and 30 degrees Celsius? Sure, you could have 20.5 degrees. You could have 22.5 degrees. So, because those half amounts are possible, we are going to connect the dots. Let's look at our graph again here. So, our initial amount, aka Y-intercept, is 20. We remember that the Y-intercept is just called that because, duh, that's where it hits the Y. Now let's find our slope, also known as our rate of change. That is the rate at which the data points change. And remember, you do that by gauging your horizontal change. So I'm going to hop over from this point to this point. I would have to hop over 1 to the right, which makes that a positive 1. To go from 25 up to 40, that means I hopped up 15, because we know that rate of change is your rise over your run. This is going to be 15 over 1, and they're positive 15 and a positive 1 because you hop to the right and then you hop up. So here we have our Y-intercept. Here we have our rate of change. I've talked to you in previous videos, but this is just a reminder about how when the data form a straight line like this, hopefully we remember, what's the word? Hopefully you guys all at home said linear, okay, that we can automatically know, because they form a straight line, that the rate of change in between every data point is 15 over 1, because in order for it to be linear, it has to have the same rate of change in between each data point. So we know that the rate of change for the whole graph is 15 over 1 just by virtue of the fact that it's linear. And again, just like our last example, look. So we've got our initial amount, aka Y-intercept, here in the equation. We have our slope, aka rate of change, here in our graph and in our equation. So again, this verifies why we call this type of an equation slope-intercept form, because it contains both our Y-intercept and our slope in it. Now I will say that more commonly you'll see the slope part written first, followed by the Y-intercept. So the type you're going to see in textbooks more often is this 15x plus 25. But we know from commutative property that that's exactly the same thing as 25 plus 15x. So that helps to explain why this is actually called slope-intercept form. Let's use the example that I mentioned to you guys a couple minutes ago, just to review all this and make sure we're all on the same page. So I'm going to go back to that situation I was telling you guys about, where because you're so awesome, I'm paying you $5 as soon as you walk in the door, plus $1 for every minute that you behave. So I'm going to graph just a few data points on here. We've already established $5 is our initial amount. So after 1 minute has passed, you're going to get another $1. So that means your minutes are going to increase by 1, your dollars are going to increase by 1. So I'm going to put a data point right here. If your minutes increase another 1 minute, your dollars are also going to increase another minute. If your minutes, you're going to increase another $1. If your minutes increase by another minute, you're going to get another dollar, etc., etc. So for example, if you behave for 4 minutes, you get the original $5 that I promised that I gave you as soon as you walked in the door, plus another $4. So if I were going to write an equation to represent this situation, well, it'd be pretty straightforward. First of all, x, our number of minutes that you behave, is our independent variable. Y, the total amount of money that you make, is your dependent variable because it depends on the amount of minutes that you behave. So to find our total amount of money, Y, we take our original amount, $5, plus we add the number of minutes that you behave because it's $1 for every minute that you behave. So technically we could say that you're adding $5 to 1 times the number of minutes that you behave, but really 1 times x is exactly the same thing as just plain x. So y equals 5 plus x. Now let's look at a couple of characteristics of the graph. So we've already talked about initial amount. So every single time I'm going to look at my rate of change. So go from this point to this point, I hop over to the right one, and I go up to, hop over to the right one, it's positive 1, hop up 1, sorry, I think I said 2 a second ago. So it goes over to the right one, and then it goes up 1. So for my rate of change, rise over run, that's a 1 over 1, which simplifies to a 1, if you think about it. So technically, some of us might think, well in this example, slope-intercept form didn't work because we've got our y-intercept in our equation, we've got a 5 for our initial amount, but we don't have our slope in our equation right here because our slope is 1 over 1. Well, technically, like I just said, you could technically write x as 1 times x, and since the slope always seems to show up right here in front of the x variable, really this equation is in slope-intercept form. It's just that we don't bother to write the 1 there because it doesn't really change anything. So I have actually taken this data and written it in the format of an equation and in a graph. Depending on how I decide to pay you guys, we might connect the dots or we might not, because I might decide, well, I'll pay you for every half of a minute, or we can certainly have a fraction of a dollar, because we could have $5.50, so the values in between 5 and 6 are possible. So we could go ahead and say, yes, we will connect the dots. This arrow right here means that technically I could keep graphing things forever and ever and ever on this graph. It just extends outwards. Of course, there's no such thing as negative minutes, so we don't have any values that extend past that 5 right there. So hopefully this helps you to see a little bit of the connection between how you could get an equation from your graph, because it gives you your y-intercept and your slope and a situation, and you can transfer your data from a situation to a table of values like we just did, to a graph, to an equation with no problem.